All right. Hello, everyone. Good afternoon or evening. Thank you for joining us for another meeting of Physics Journal Club. And our speaker today is Khanal, and he will talk to us about some interesting stuff concerning nuclear stars and all of those details. And I hope everybody has gotten a chance to just review the paper. If not, we'll still go on to discussion. And just give you a heads up, you may want to take notes because there will be a quiz afterwards. And there's a book prize for the person who has the highest score. So only one winner. And yeah, that's it. And so without further ado, let me hand it over to Om, go ahead, you can share.
Thank you, Manqoba. You can see my screen, right?
Yes, but we cannot see you.
Don't worry. Okay. This is the paper that I'm going to discuss today. You can see if you need some citation or if you need some reference, here are the links I have provided. Okay, let me get started. Okay. This thing. So how to remove this top panel showing things like stop sharing, pause? Do you have any idea?
What?
This top panel, because it's blocking some of the content.
Oh.
Can you just hit the got it button?
What?
Can you just hit the button that says got it?
No, there is no guarded button. I mean.
Oh.
I think we can see now. We see outline at the top.
Okay, okay. So this is the outline of my talk. I will start with something we were familiar during our high school, that is equation of state, and I will move to a little more complex term or complex factor in equation of state. And then I will introduce symmetric energy. I will talk the importance of symmetric energy in astrophysics, the density dependence, its density dependence, and how do we probe or how do we study symmetric energy and why we are interested in it. And then I will go through the experiment in details. I'll go through the experiment in details that's described in the paper, and then talk about the collision, because the experiment is based on the collision of heavy ions and the observer of the collision. And finally, I will discuss about the results and conclusion. Okay, so this picture here I'm showing the neutron star merger, and this is interesting picture because if you haven't forgotten, then recently in physics Nobel Prize was given to the detection of gravitational wave, and that gravitational wave was emitted from such event, like from the event of neutron star merger. So now we are going to neutron star. By neutron star, it means it has high concentration of neutron, and this neutron star is complex and very interesting stops in the space that people are interested to study because of its variant density, because of its complexity, and also it's difficult to create such kind of difficult to create the density that we found in neutron star in Earth. Like it's impossible to get that, but we can create such events, such density in lab, and we can that's how, I mean, we can study the events behind a neutron star, or we can try to study the physics of neutron star. Actually, the tool that we are going to study the physics of this Newton star, where I'm going to discuss in the following slide. This will be the main tool that the whole paper is based on. And moving to the another slide. So here, after talking about little about the Newton star, I'm going to talk little about the anatomy of Newton star. As you can see, this is the anatomy of Newton star. In the core, it is highly dense. It has a lot of stops in the core, and the equation of state influence different parameters or different stops in the stops of the Newton star. And the Newton star has the radius of around 11 kilometer, and the mass is around 8 to 20 solar mass. So small stops, you see the 11 kilometer circle or sphere. Let's assume 11 kilometer sphere with highly dense stops in the center, in the core. So it's interesting. So people are interested to know more about this, the physics inside the Newton star. And let me move to the another slide. So this is the thing that we are very well known, the equation of state for ideal gas. We have studied the equation of state for ideal gas, and if you look these pictures, these are the some relationship between different parameters at different conditions. So these are the relationship between pressure and volume and pressure and temperature for the ideal gas. And not only ideal gas, equation of state can be used to study the properties of different states of matter such as fluid, solid, and even to the star. So when we move to the star, the equation of state is little complicated because star or the Newton star, let's talk about this. By star, I mean Newton star here, or the Newton star, because it has very high degree of freedom, and there is high, as I told you, there is high concentration of the stops in the core, that is neutrons. It has neutron proton asymmetry. There is another parameter that we need to consider while studying the equation of state. I mean, the other parameters for the equation of states are energy, density, because you see the Newton star was, I mean, the radius of the Newton star is around 11 kilometer, and if you consider the radius of nucleon, it's very small as compared to the radius of the nuclear star. So when the radius is small, the volume will itself be small. But so we use the parameter density instead of volume, and the density is that parameter that governs most of the physics of Newton star. Okay, so let me start again with this mass defect formula. In this formula, you can see one term here, that is binding energy, and the binding energy is expressed as this formula according to some model, or let's say according to liquid drop model. It has a lot of stops. Now we want to make an analogy with analogy of this binding energy with equation of state, which is this. So if you look here, so here the equation of state is expressed in terms of parameter density and asymmetry. Delta is asymmetry, which is expressed as n minus g over a. If you compare the first term, so both the first term in binding energy expression and equation of state are this delta independent. The value of delta is 0 because you don't see any n minus g over a term here. So this is symmetric energy, which describes the symmetric energy dependence on density. Sorry, this is symmetric matter. I'm sorry. This is symmetric matter, which describes the the coefficient AV dependence on density. And if you move to the second term, you can see n minus g over a square, which is del square. So second term is analogous to this term, and this second term here is the symmetric energy. This is symmetric matter, and this is symmetric energy. I'm sorry for wrongly saying this before. So this is symmetric energy. It is you can see this term is dependent on quadratic on the delta, this asymmetry, Newton proton asymmetry. Now I want to show you the plot of these two terms in the following slide. So this is the plot of symmetric matter. So you have equation of state here. So this plot is representing this term. this term here, and you can see it has a minimum at some value of density. This x-axis is density, y-axis is energy. It has minimum at some value of density, and this density is called saturation density. So this curve represent the curve at delta equals to 0, and then the saturation density is 0.16, and moving to the another part of the equation of state, the symmetric energy. So this is the symmetric energy line, symmetric energy curves, or so if you take this term, the second term, and do the Taylor expansion, then you will get the equation in terms of this, where this is offset and this is slope. This L is slope and S naught is offset. So if you draw the tangent in these different curves, then you can get the values of L, which is slope. So we can say that we have slope symmetric energy and soft symmetric energy and stiff symmetric energy here. If the slope of this curve is negative, then it is soft, and positive, if the slope is positive, then it is stiff. So what we can say is that if the density dependence of symmetric energy, is positive at high density, then that corresponds to this steep curves, then what we can say that neutrons are expelled out of the system. And if the density dependence of symmetric energy is negative, which correspond to these soft lines, then we can say that symmetric energy attracts neutrons toward the system. Now, this shaded region here is the experimental constant, and you can see that at lower density, all of these lines passes through the experimental constant, but at higher density, these lines passes differently. So we are interested in this region, that at high density region, where is the region of neutron star. The neutron star lies somewhere in this region, so we want to expand this constant towards the higher region by different observable. And in this paper, the authors are taking Pion spectra at the observable to constant this symmetric energy at high density. As I already talked, the neutron star radius, I showed you the anatomy of neutron star. Now, here I want to compare the neutron star with one of the nucleus, let's say lead here. So if you look here, it is also highly, in the internal structure of lead has nucleons. They are highly dense. It's highly dense, which is similar to what we have here. Now, in order to study the physics of neutron star, we need to get a system which has the density comparable to what we have here, even though the radius are not comparable between the nucleus and the neutron star. So what is the tool to get such density is, if we collide, or if we smash neutrons to make in the collision of the heavy ions. If we collide two heavy ions or more heavy ions, then we can get the density comparable to what we have in neutron star. If you look this table, then so this table shows you the heavy ion collision of lead. You can see the density are almost like comparable here. So people, what they try to do is they try to do the heavy ion collision experiment, taking different detectors, improving detectors, and taking the different observable and trying to constant that symmetric energy at high density in order to understand the physics that happens here. So this is the theoretical simulation of the collision. You can see here, I'll play the video. You can see here how the collision happens and how the fragments are ejected. High energetic particles are ejected first, and followed by the low energetic particles. You can see here. So this is the snapshot of that video. So we are interested in the head-on collision or the center reaction. Why we are interested in center reaction? Because through center reaction we can achieve high density and high energy. And the reason we need high density and high energy, I will talk in a while. So from such collision, we get the delta resonance. That means if proton and proton collides, we get positive pions. If neutron and neutron collides, we get negative pions. And this is the yield or multiplicity of the pions. The yield of the pions, according to the delta resonance, is proportional to the square of the density. So why we are interested in pions now? There is a question like, why we are interested in pions? Because I told you the pions are produced in high energy and high density collision, and they are produced early. And they are supposed to they are not supposed to exchange the charge, or they are supposed to less likely scattered. And also, as when I was talking about that symmetric energy curve, I explained that the stiff symmetric energy expel neutrons, but the stiff symmetric energy expel less pions as compared to neutrons. So pions are one of the good observable to constant symmetric energy at high density. Moving on to the experimental details, like you see, we have a combination of beam and target, different combination of beam and target. So this combination gives us neutron rich system and neutron deficient system. That means we can get variety of density over there. And then this is energy, which is high. And this experiment was taken at this facility. And the detector used for detecting light charge particles is aspirate, the TPC, that is time projection chamber. And this is the picture of overview picture of the time projection chamber. You can see the beam, radioactive beam is coming here, it gets the target over here, a collision happens and the particles are produced. You can see the tracks of the particles. The particles are traveling in different direction, and the detector detect those particles. And the identification of particles takes place based on the stoppage power, delta energy, over like how, the du over dx. That means the energy depends on the stopping path, or how much it travels before it stops, and how much energy is emitted when it on stopping the particles. And also the particle identification depends on magnetic rigidity too. Like if you look this picture, this is the PID picture. Like you have different particles that falls in different regions. So based on this, we can identify that, we can say that the pions region is this. You have proton, deuterium, tritium, helium, and other particles over here, and we are interested in this region where we get pions. This is how we do the particle identification based on these two parameters. Okay, so once those particles or pions are detected, so the yield of the pions, dm over dpt, versus the transverse momentum pt, is shown in this curve for different systems. You can say that these two paths is for neutron rich system, and these two paths is for neutron deficient system. And this is the yield of pi minus, this is the yield of pi plus. And we have the transverse momentum here. By transverse momentum, we mean the momentum perpendicular to the beam, and this transverse momentum is associated. This transverse momentum is associated with the physics, underlying physics within the system. And if you look this curve, you can see that the maxima values for pi plus and pi minus for different systems are different. Like you have the maximum. Just focus on the dots. Okay, let's forget these colorful lines for a while. I'm just focusing on the dots at this time in this slide. So these dots are the experimental data. You can see the maximum value is different here. So this difference is maximum. This difference in maxima is due to the Coulomb influence during the experiment, because the pions are charged particles, so there is the presence of Coulomb. Also now we, as I told you, these dots are the experimental data. Now we need to compare this experimental data with the theoretically simulated plot or theoretically simulated data. For the theoretical calculation, we use the transport model, which simulates the particle passing through the nuclear matter, and this model is highly used for heavy ion collision. So these red, now let's focus on this red and the blue lines. These red and blue lines are the theoretical simulation curve, the blue line is drawn without considering the Pion potential, and a red line is drawn with considering the Pion potential. If you look this figure, for lower value of transverse momentum, this blue line under predict the data. You can see here, all of this blue line is falling below the data. And this under prediction is long for pi plus as compared to pi minus. And if you look above 200 MeV per C, these lines are somehow agree with the experimental data. Like we can see, the Pion potential does not influence these lines with the experimental data too much for the reason greater than 200 MeV per C. And these theoretical calculations were done for the value of L. You know, the L means, I already showed you the slope of these lines, that is the slope of the symmetric curve. The value of L for these lines is 80 MeV, and the effective mass, which I'm going to tell you in a while, for this simulation is 0. By effective mass, I mean the mass difference of neutron and proton. And actually, we need to take the momentum dependence of symmetric potential for this curve. And momentum dependence of symmetric potential is difficult to determine. So we use a trick of calculating equating mass using effective mass, because effective mass gives the momentum dependence of symmetric energy. So here's a trick of using effective mass for these theoretical plots. Okay, now the yield is taken in the form of ratio. So this is the single ratio. This is for neutron rich system, and this is for neutron deficient system. And these, you can see different plots of different color and different format. So that represents different combination of L and effective mass. So you can see the single ratio, it has a rise at the low value of this transverse momentum, and this rise is due to the opposite Coulomb force experienced by the pions of positive and negative charge. And all these curves under predict the data below around 50 MeV per C and over predict the data around 150 MeV per C. And if you look which system is more sensitive, then you can see that at higher value of transverse momentum, this neutron rich system is more sensitive, because you see the experimental data is lying within the range of theoretically simulated curve when you compare this area and this area. So we can say that neutron rich system is more sensitive at higher value of transverse momentum. And this is just to keep you remind that we are talking these plots, we are taking these plots at different values of L, and by L we mean the slope of these lines. And this is how the single ratio was calculated. And you see, this is more sensitive rather than this, and there is the disagreement in sensitivity in difference in these two systems, and this is due to the inaccurate treatment of Coulomb and Pion potential. Now, if we plot these values of L and effective mass, we get the correction counter here. This is the correction counter extracted from the single ratio. And you can see that the shaded region lies within the 68% of confidence level, and this dotted region lies within the 95% of confidence level, because it is in 1 minus sigma and it is in 2 minus sigma. At delta m star, that is effective mass, equals to 0, the values of L was obtained to be this, and the slope was obtained to be this. And these values are consistent with the constant extracted from another observable using the same model. Now, after talking about the single ratio, I am jumping to the double ratio here. So double ratio is the ratio of single ratio in one system to the single ratio in another system. So this two figure is equivalent to this. Why we need double ratio? You may think of that, because when we talked about the single ratio, why we need double ratio? So you see, in single ratio, you have some problem with the sensitivity to the column, right? Those single ratio were sensitive to the column interaction, and this double ratio removes that sensitivity, and also it removes the sensitivity to the acceptance difference of pi plus and pi minus. So the acceptance rate of pi plus and pi minus is more improved by double ratio than by single ratio. Now focusing on this curve, if you look, the consistent region lies within this. So in this consistent region, we get the value of L, that means the slope of the symmetry curve, to be this, and effective mass to be this. So we talked about the experiment, the observer, collision, and then pions were the observable, right? And then we calculate some single ratio, we calculate some double ratio, and at the end of the day, we are concluding by the following conclusion: like the symmetry energy at suprasaturation density were constant for the transverse momentum greater than 200 MeV per C, and tighter symmetric energy constant were obtained with L lying with this in this range and S not lying with this in this range. And although we have some constant at higher density from this experiment, more further constants are needed in order to get the better value of L and S naught. Thank you.
Thank you very much, for that presentation. I will now hand it over to Dr. Chajecki to sort of moderate any questions that we have and sort of moderate that discussion section. Dr. Chajecki, if you are ready.
Yeah, well, it's an open floor, so if you guys have any questions, that's a good time to ask.
So, I have a question. In the
Okay.
paper also, I saw that, and on one of the slides where you explain the experiment, it talks about the beam energy, and it says it to be, yeah, one more slide before
Yes.
that. Yep, this one.
Yeah.
It talks about 270 A MeV. What is that capital A indicating?
Okay. A is the number of nucleon. Like we talk energy per nucleon, right?
Oh, I see. Yeah, yeah, that was something I never understood.
Yeah, another notation would be MEV by U, so it's MEV per nucleon.
Yeah.
All right, thanks.
Mm-hmm. Yes.
I have a question about the transport model that used in the simulation. Actually, I don't know what it is a transport model. So can you just maybe talk more about how we use it, how it is derived,
I would
and
love
what
to
assumption we're
to
using?
talk about this skin, but I also don't know much about this model. I haven't got chance to learn this yet.
Well, in short, the transport model simulates the particle passing through the matter. And depending what matter you put in this case, for example, if you're simulating those collision thin on thin, when the system collides, then the particle starts being emitted, but those particles, they're still gonna interact with the matter. And depending on the cross section and so on. So the transport model, in general, the word transport model comes from the group of models that simulate the particle passing through the matter. So particle interacting with other particles and so on. But then you start looking at, there are various classes of models and they have different acronyms because there are different approaches. Someone else wrote the code, put maybe some physics that the other models don't have, or took some different perspective. That's when you start going a lot into the details, probably outside the scope of this meeting today. But the short story is it basically simulates particle passing through the matter.
Okay, so but when you say passing through the nuclear matter, does it is the particle affected by, I mean, is it calculated by mean field potential or just simulate by, after all the particles are created, just simulate the pairwise interaction?
No, the mean field is included, yes.
Okay.
So, I mean, it's, in many models, it's one of the options. So you're including the mean field, you're including the in-medium cross-section. For example, we know that when you measure the cross-sections, typically when people do experiments and they measure cross-sections, and you guys probably do also if you run this, if you're taking the credit hours for research in the accelerator in summer, well, not during the pandemic, but before that, Asgar used to do some scattering experiments. So you can measure the cross-section, but it turns out that the cross sections for those reactions, when you have in medium, they are typically lower, and so different models treat them differently. But yes, you are right. The mean field is included in those models, and depending on the approach, you can also how far they want to simulate the particle passing through the medium. Because do you include two-body interactions? How far you go in terms of the interactions. Things are, of course, getting more complex and much more heavier on the calculations, on numerical calculations. So there are some variations. But yes, you are right. The mean field is, I didn't want to use that term because it's very nuclear physics.
Oh, thank you.
Particle, yeah. But a very good question.
For me, I have a little bit more general question. When I tried to read the introduction, I couldn't extract the main question that is addressed by the field in itself. So I understand that generally you have a star and it collapses. It either becomes a white dwarf, a neutron star, or a black hole. And now you're looking at neutron stars. And when you zoom into neutron stars, what you are interested in is the equation of motion at the surface, or that's what they say in the paper or something like that. But anyway,
the equation of state.
Oh, the equation of state.
Yeah.
Why am I saying equation of motion? I'm into nuclear physics, sorry. The equation of state. And so it has multiple parameters. You already know how it relates to the density of the nuclear matter, but you don't know the microscopic parameters.
Well, you don't really know how those.
I mean,
so this is
yeah.
this is part of. Oh, sorry. Why don't you try to answer?
Yeah, I'll try first. Like you don't know at high density. Okay, so if you look this figure, I'm showing like there is the experimental constant at lower value of density, and you are interested in higher density. Okay.
So you are interested to know what is the equation of
I mean,
state at higher density.
Yes,
Is that the-
yes.
Well, in other words, the question is how much do we really know about the neutron star? Okay, we're talking. People got the Nobel Prize for collision of neutron stars, but we don't know much about neutron stars themselves. And this is one of the side, for a lot of, for like our process, how the heavy element were created. So the neutron stars in general are of interest for various reasons. And people study neutron stars looking at various things. For example, some people study just the crust of the neutron star, like the outer layer and the nuclear reaction in that crust. Some people go, lower, more to the core, to the neutron star. The whole point is that all those people and all those different physics observables, they have to be governed by the equation of state. Okay, our equation of state for any physical system, it's like a holy grail. Okay, it's ultimate goal, because when you know it, you know everything. Okay, of course, for ideal gas, that's what I mentioned. It's simple, right? But it's simple. It's nice because it's nice that it's simple because you can understand those relations. But it gives you already a lot of predictive power, right? Because when I tell you that, tell me temperature of your ideal gas when you double the pressure by a factor of 2 and keep the volume constant, right? Just by this equation, you already know what's going to happen. We would like to have the same thing For the nuclear matter, the problem is it's not that simple, right? Because for the ideal gas, it's ideal for a reason, because it doesn't really exist, right? The particles don't interact with each other. There's only one type of particle, so they just bouncing from each other like tennis balls, and that's your kind of, but they have no masses. So there is a lot of assumption with those ideal gases. In nuclear matter, even if you just think about neutrons and protons, right? They already, one has charge, the other one doesn't have charge. They interact differently. The cross sections for each of them is different. Then not only that, the potential depends on how fast they're moving. So there is so many levels, and then you start adding neutrons, and you start adding the dense matter. Like there's such a high level of sophistication and difficulties as well, that coming up with the equation of state is not a trivial thing. Okay, and to make it even worse, I cannot make the neutron star in my lab. There's no lab on the Earth that can make neutron star, right? But it's similar like when we predict the weather in 2 months, right? We take all the information that we have, we use the models that seem to be working, and then we predict the weather. It's not much different here. Well, there's a lot of similarities. They are different. There are a lot of similarities that we're trying to predict what happens with the neutron star without ever being able to create purely neutron matter. But what you're doing, you're basically studying nuclear physics by adding more and more neutrons. And that was one of the purpose of this experiment. If you look at the list of, if Om was talking about colliding tin, but for you colliding proton-rich tin means where the number of neutrons and protons is the same, and then you start colliding isotopes of tin when you keep the constant number of protons, but you start increasing number of neutrons. So you basically understand how your physics evolves with the increase of neutrons, and then you go as far as you can in the lab, and that's one of the reasons why we have this new big facility at MSU that has been recently finished, because we want to push as far as we can as human beings, and then the rest we just extrapolate. Okay. But as you know, extrapolation, you carry the error bars that you have. So when you extrapolate, you want to extrapolate from something that you measure very accurately and very well. Because 10% error bar, if you have to extrapolate miles away, it doesn't really teach you much. And that's basically what you can see by those lines. When you start looking at the density on this slide, you go above 1, 2 is where we believe neutron star is sitting. You can see those lines are all over the place. So even if you constrain low density, you really have to constrain it very tightly to be able to say something about the neutron star. The nice thing is, sorry, you asked me to talk. I can talk.
No, yeah,
but
go ahead.
The nice thing about it is that it's not like it's nuclear physics cares about it and no one else cares about it. Because actually we measure things from the equation of state. You can measure things that can be confirmed observationally, like the deformability of the neutron star, how fast it rotates, those things. That's something that observers are measuring. We're using their own techniques. So it's really different field, observational astrophysics, and what we're trying to do here, it's a completely different approach, but we have some common denominator and some common interest. We just take it from different angles, because all they can do, they can observe. All we can do is we can smash things and learn how the nuclear matter behaves at those high densities and high neutron asymmetries.
Great, thank you for that well and detailed answer. I had one.
I can stop sharing, right? Or you
No, please don't stop.
Okay.
Please, I had one last follow-up question. I didn't understand the parameter, which is the single ratio and the double ratio. How does that connect towards? Because you talked about different parameters at the beginning for the equation of state. And how does measuring those ratios relate to your grand purpose of that you mentioned?
So you see, firstly, we have this experimental observable data, right? These dot lines. So, and these are the different theoretical calculations. Okay, so at this plot we have like 4 theoretical calculations for the different values of L and effective mass. So this was, and then you see these 4 calculations are the best fitting here with the
I don't
experiment.
think, sorry, I don't think that's what Manqoba asked, right?
Yeah. So I'm just asking that parameter, how does it fit?
No, I mean at the end of the day we use these things to determine the value of L and S naught.
But
Oh,
Manqoba is asking why you're looking at the ratios.
yeah.
Why do you looking at the ratio of pions? Or is it what you ask?
Yeah. That's pretty much, I couldn't make
Uh-huh.
that connection myself. That's what I was asking.
Okay, so for that, like why you are looking at the ratio of the pions, right?
Weren't you saying it determines that?
Yeah, can you go to the previous slide?
Okay.
Okay,
Maybe I can help you. Previous one, when you're showing the spectrum.
this
So
one.
yeah, no, when you're showing the spectra. I asked you previous, you keep going
Okay.
the same slide. Here.
Yeah.
So
Okay.
Manqoba and others. I mean, think about black body radiation. Okay. If you measure the spectrum, like energy spectrum of the black body radiation, it kind of has exponential distribution, right?
Mm-hmm.
Okay, just going, and you can see you have a little bit of peak at low momentum. I mean deep low momentum that comes from the Coulomb, and then it basically goes exponentially. If you look at the scale, you go through the orders of magnitude. Okay, you can see there are 2 orders of magnitude that you're crossing, going from low momentum to high momentum. Okay, you with me so far?
You mean this one?
You look at the x-axis, you can see 10 to the minus 3. The axis is logarithmic axis.
Oh, okay.
It's 10 to the minus 3, 10 to the minus 4, 10 to the minus 5.
Mm-hmm.
If I tell you that symmetry energy or any other effect, if it's 10% effect, you won't see the difference whether I have 10% more or less if you're plotting it in the logarithmic scale. Okay. So the idea of making the ratio is that imagine there is some underlying physics that is in your spectra includes, and there is a lot of other things, not just symmetry energy, dynamics and other things. So I said I just want to separate it. I just want to separate my symmetry energy from everything else. So what I do is I measure, I have the same isotope, that means I have the same number of protons, means I have the same Coulomb basically. So I measure pions and the same I measure negative pions, I measure positive pions for the same system. So I can assume that they have the same underlying physics, and the only difference between them is going to be due to the symmetry energy. Okay, so if I want to focus just on the difference, you can either calculate the difference or take the ratio. Calculating the difference, you're still going to be dealing with different magnitudes. So it's a basically practical approach. I simplify it a little bit, but the basic idea is, how do I look at something that is of 10% effect for the variable that varies across 2 or 3 orders of magnitude? So it's actually a typical approach in many fields, in condensed matter, other. If you have observables that varies across orders of magnitude and the effect is small, you want to focus, you want to just have a way of showing the data that emphasizes this small change. And that's what the ratio is going to give you.
Great. Thank you. That answers my question. All right. If anyone else with a question before we move to the quiz, is supposed to be like 5 minutes, and Kushi can post it in the chat.
And I can leave, right? I'm not taking the quiz.
Yes, yes. Thank you.
Yes,
Okay,
Thank you
guys,
very
enjoy
much.
the rest of
Thank
your
you.
evening, and thanks for
Yeah.
having me. Bye bye.
Okay.
Thanks.
Thank you.
Bye.
Thank you. Yeah. Right. And then Kushi, you can share your screen and walk us through some some student opportunities.
So I've posted the link in the chat. Do we want to give 5 minutes for writing up the chat, or should I start with the opportunities right away?
I think so. It's good to give some time.
Yeah,
Okay.
okay.
Yeah. Let's
Yeah,
let's
it's
give
47 right now, 4:47. I'll think about giving 5 minutes. So at 52, I'll start talking about the opportunities that I've got.
Oh, you make these questions really hard.
Is that? I think I discussed most of the things here.
He probably means you have made it very simple.
Wow. It's such tricky questions.
Are you participating, Manqoba?
Yeah.
Only I am not participating because I made the quiz and answers on the form. So
I mean, I also can't write.
Wait. Oh, I think there's a question that there's a problem, but we'll discuss when we're done.
I know that.
So we gonna find the result right now, or
Yeah, we are going to find out in just 2 minutes. I
Okay.
think everybody should have completed the quiz.
Okay, then
I'll give 1 more minute. It's okay. I'll give 1 more minute. Last 1 minute.
okay. Oh, interesting. I can view my score.
Oh,
So who won the prize?
Dave.
Is everybody done with the quiz?
Tell us, please.
Okay, let me check it out.
I got 40, in fact. I don't know. I got one.
That means you got one wrong.
Yeah.
Is that true?
Oh man, I did an arithmetic mistake.
You also got 40?
10 kilometers is
Yeah,
you put it in meters.
No, no.
Why you putting it in meters?
that confused me.
Kushi, announce.
Okay, I'm looking at it. Give me a moment, please.
That's
Yes.
why I call tricky, Manqoba.
It was.
I need book. Which book do you have?
Ken, are you done?
Just 1 second, please.
Yeah, but anyways, I can't get the prize even if I would win.
What do we have?
You can give it to me.
Oh no, I
Oh,
haven't won.
wait. There is one person with 50 on 50 points.
What? Really?
Get that.
Keen,
Who should be the one?
Brendan. Oh, wait, speak.
Uh,
So
Prakash, what's your score?
50.
Oh, congratulations. Oh, Prakash.
So yeah, it's Prakash, 50 on 50. Congratulations. Here is my emoji, the clapping emoji, and celebrations for Prakash.
Oh, thank you.
All right, cool. So I'll quickly go ahead and share my screen.
Which
Prakash, you
book is he
should
getting?
contact Manqoba for it. So we are yet to get the book from, we get the book from department. Once we get
Oh,
the book, we'll
okay.
pass it on to you. Manqoba will give you more instructions on how and when to collect it.
So we all should get a party from Prakash for the winning.
Thank you.
Yeah, a cup of tea, Prakash, for everybody.
At least.
I love tea.
Yeah.
Little bit hot.
okay, let's move on to the grad student opportunities. Then we can still hang around and chat.
Manqoba? Okay.
Yeah.
Oh, someone already started. Okay, that's fine.
Yeah, go ahead, Dave. You can ask your question by the time I start.
It's not
What else?
questions, it's more like a comment. Om told that the Nobel Prize was given for this Newton star merger, right?
No. I told for the
For
gravitational wave.
measuring the gravitational
Wave,
waves.
that was emitted from the Neutron star merger.
Well, was that from Newton star merger or
Yes.
from black hole merger?
Neutron star merger.
Star, I think, yeah.
It was Neutron star.
Mm-hmm.
But there was a big news, that 30 solar masses black holes were
That was the initial one.
yeah, on 2015 or 16, and there was a huge news. I don't know. Yeah, maybe.
Yeah. Recently there was a Newton star merger.
Okay, then later on they detected more and more. Okay. Right.
Recently.
So you should be updated there.
No, I mean, I'm asking you, that's why.
Okay.
You are the one in charge today. Okay, that's all.
Okay, then I'll take over from now. And initially we introduced this section as grad student opportunities, but we have eventually got some undergrads attending it. So now today I'm calling it just opportunities, just straight ahead. So the first thing I'm going to share, oops, why can't I can't. Okay, so the first one thing I'm going to do before I do anything else, I'm sorry. So this is something I'm trying for the first time. I don't know how that is going to work. I'm going to post several links on the chat, and now I'm going to start sharing my screen and tell you what that is going to be. You can ignore the chat for now. All right, so the first one that I have on my list is the Qiskit Global Summer School for 2021. And it is very simply laid, especially for high school students. So if we have any undergrads who are interested in joining this, they can. And if there are any highly motivated grad students who are also willing to parallelly learn about quantum machine learning apart from their research, if it is not quantum machine learning, they can also try getting in here. And the first link in the chat corresponds to this. The second thing I have is DTP 2021, which is a conference on high energy and nuclear physics within quantum technologies. The registration is open and it's going to stay open till June 6th. So the second link in the chat corresponds to this one if that interests you. The third thing is an international conference for atomic physicists. It is going to happen virtually this time, and it includes photonic, electronic, and atomic collisions. The early bird registration has opened up, which is going to stay open till 18th of June. And the third link in the chat takes you to this one. The next one, if someone is graduating, I'm trying to indicate towards Om if that applies. So then there's a research associate position in
I
FRIB.
mean, this email was sent today, right?
Yeah. And ZB just mentioned that this facility has been completed and they're looking
Yeah.
for someone who has a PhD. I'm a little far away from this, so maybe if you are close enough, then this is for you, Om. Then there are some small things which I would like to share, which I felt it is cool and I have done it, so I'll just share it with you. There's something called WMU Signature Program. Because there are no undergrads, I'm just assuming, correct me if I'm wrong, I'm going to explain it in terms of grad students. So they have this 4 steps here. And because we are grad students, we don't have to go through the first step. We can directly jump onto the second step, which is declare pathway. There are 9 pathways given. And most of our grad students are serving as teaching assistants. So this last pathway of teaching and student success is easily achievable for us. Now, why do we need to do WMU signature? There are several activities, events you need to attend, write some short reflections, 2 pages, 3 pages, something like 1 page for each event, something, or sometimes 2 paragraphs for one event. The best part is when you graduate, your certificate will have this extra line indicating WMU signature along with the pathway. So when you go ahead looking for jobs or some position, that will make you a little distinct compared to some other competitor who has exactly same qualifications as you. Okay, so that is one thing. I think it's the next link in the chat, which will take you to the WMU signature page. If you need to know more, I have completed it with teaching and student success. So if you have any questions for me, I'll be happy to answer in the end. And then comes next is the graduate student teaching intensive. You'll be like, Kushi, why are you sharing an opportunity from last year? The only reason I'm sharing it from last year is because this event, I would recommend all the first year students, if this is your first summer and you're not doing something great, then do catch up on this if you are passionate about teaching. The reason I'm sharing is because it says that the nominations are accepted till July 15, 2020. So for this year also, I'm hoping that they are accepted till July. You cannot nominate your own self. So if you are interested in this program, ask Dr. Corista. He'll be happy to nominate you. I think department can have 2 to 3 students nominated each year. So you can try attending this. And now they have extended the program. Initially, this is like a 1-week professional training program where you are taught several different active learning methods and inquiry-based teaching methods and their benefits. But then there is 1-year mentorship program, which you can extend. And that year-long mentorship program helps you develop an online portfolio for you, which will have a teaching section, a research section. You can have all your things put up and they'll guide you how to make it look very beautiful and greatly presentable. The next thing on my plate, which is the last thing, is the STEM instructional program. So it usually works through this Howard Hughes Medical Institute's grant that we had obtained. We means WMU had obtained. And to show you something interesting, I want to click on that hyperlink and show you this picture. So you might have some faces that you already know. Don't forget Manqoba here in the corner. And we have one grad student called Mariam, so she's here. And that's me, which means we 3 have attended this. Initially, it's a 2-week professional training program, and then it's a year-long mentorship program. So that one helps you again with how to teach better and everything. It enhances your profile for academia, if that's your goal ultimately. And this one also has a year-long extension, which will help you in building it better and improve your teaching style in the labs that you are teaching actually in physics department. So yeah, I think that's all from my side. I'll be looking for more opportunities for sharing with you for the next time. And thanks for today.
Thank you very much, Kushi. And once again, let's thank for the lovely presentation. Thank you. And I would like to encourage all the other people who are hiding to come out of the closet and do a presentation. It helps a lot. We learn, and I think you also learn. Otherwise, thank you guys. Have a good day. I will stay around if people want to chat and do some things.